Hi, Assalamualaikum and a very good morning. So now we are in chapter 7, Ionic Equilibrium, and we're going to focus on the subtopic of 7.3, which is the Solubility Equilibrium, part 1 of the video. So in this video, we're going to learn about the definition for the solubility, molar solubility, as well as the solubility product. Next, we're going to learn about the calculation for the KSP from the concentration of the ions. Last but not least, we're going to predict the possibility of the precipitation of a slightly soluble ionic compound by comparing the values of Q with the KSP. For the learning outcome of D and E, we're going to look about that in the next video, which is in part 2. So without any further ado, let us start with part 1 of the video first. So solubility. Solubility basically means that it is the amount of the solid that is required in order to form a saturated solution in a specified quantity of a solvent at a given temperature. And the solubility will have a unit of gram per dm cube or gram per liter. And of course, the solubility will be depending on the temperature. In a usual case, the higher the temperature, the higher going to be the solubility. However, for our syllabus, we're just going to focus on a given temperature, in which it usually happens at room temperature, which is about 25 degrees Celsius. And the solubility can also be quoted in terms of the molar solubility, in which we're going to look about the number of mole of the solute that is present in 1 liter of the saturated solution. Okay, and it's going to have the unit of mole per dm cube or mole per liter or molar. Alright. So solubility equilibrium. So in a saturated solution, the undissolved solute, which is the ionic solid of AgCl, will be in equilibrium with its ion, which is the Ag plus aqueous ion, as well as the Cl minus aqueous ion. And it's gonna be in the equation as shown as here, where the AgCl solid will be in equilibrium with its aqueous Ag plus aqueous ion, as well as the Cl minus aqueous ion. And the equilibrium gonna be achieved. And in a saturated solution, it's basically described a solution that contains the maximum amount of the solute that is dissolved at a given temperature. And at this point, the undissolved solute and the dissolved solute, which is the ion, are at the point of equilibrium. And since we know that they are in the states of equilibrium, we can write the Kc expression, in which it is equal to the concentration of the product, which is Ag plus, multiplied by the concentration of the another product here, in which it have a stoichiometry of 1 and 1, so it's going to be to the power of 1 and then to the power of 1. And for the AgCl solid here, it will not be included inside the expression. And this Kc here is basically equal to the KSP product. So the solubility product KSP is basically the same as the Kc, in which it is the product of the molar concentration of the ions involved in the equilibrium, each raised to the power of the stoichiometric coefficient in the equilibrium equation. And as usual, the KSP will actually have its own specific unit, but in most cases, which is in this chapter, the unit gonna be ignored. So now, let us look about how we can apply the concept that we have learned, which is the molar solubility as well as the solubility product into an example. So for example, number 1, the solubility of the PbI2 is 1.2 times 10 to the power of negative 3 mole per dm cube. So this solubility is in the unit of mole per dm cube, in which it refers to the molar solubility. And we have to calculate its solubility product, where this term here refers to the term of KSP. So first thing first, we need to write the equation for the PbI2. So the PbI2 in a saturated solution, which is in the solid state, it will be in equilibrium with its ion. So the PbI2 will be forming it Pb2 plus aqueous ion, as well as the I minus aqueous ion. And since we have two I2 here, so we're going to balance the equation by writing 2 at the front of the I minus, so that the equilibrium so that the equation is balanced. So first thing first, we need to write a balanced equation which is in the states of equilibrium. And once dissociated, at equilibrium, it's going to produce S concentration of the Pb2 plus aqueous ion, and then it's going to produce 2S concentration at the equilibrium. And we can let the molar solubility to be S. So we can say that the KSP, if we were to write that, we're going to get Pb2 plus multiplied by the concentration of I minus to the power of 2, because it has us like the coefficient of 2. So the Pb2 plus here is referring to the concentration of at equilibrium to be S. Meanwhile, for the I minus, it will have a concentration of 2S, and then we need to include the power here. And then we can substitute the value of S, where the value of S is gotten from this question, which is 1.2 times 10 to the power of negative 3. So S is equal to this value, and then 2 times S to the power of 2. Once we solve that, we're going to get the solubility product to be 6.91 times 10 to the power of negative 9 without any unit. Alright. Now we're going to look into example number 2. So for example number 2, the solubility product KSP for calcium carbonate at 25 degrees Celsius is 2.8 times 10 to the power of negative 19 m squared. We have to calculate the solubility of the calcium carbonate in gram per dm cube at this temperature. Okay, so the KSP is being given. So as usual, when inside a saturated solution, you can say that, for example, let's say if we have the CaCO3, which is in the solid state, it will be in equilibrium with its ion, which is the Ca2 plus aqueous ion, as well as the CO3 2 minus aqueous ion. So it's going to be in this equilibrium. Okay, and at equilibrium, it's going to be dissociated in order to form S as well as another S solubility. Okay, and we can let the S to be the molar solubility. So we need to figure out the value of S. So we know that our KSP is basically equal to the concentration of the aqueous ion multiplied by the another product, which is the CO3 2 minus, and then this KSP value is given as 2.8 times 10 to the power of negative 9. So Ca2 plus is equal to S, CO2 3 minus is equal to S. So we multiply that together, we're going to get S squared to be 2.8 times 10 to the power of negative 9. And then we're going to set the value here. And lastly, we're going to get the value of S, which is 5.29 times 10 to the power of negative 5 molar. So the unit need to be included because you are talking about the molar solubility. Okay. So from here, we have calculated the solubility, which is the molar solubility. But then the question asks us to write that in the unit of gram per dm cube. So this unit here is in the unit of mole per dm cube. But then we need to convert that into gram per dm cube. Okay, so we need in this unit. So what we're going to do is that we need to multiply it with the molar mass. Okay, so we need to multiply this value with the molar mass of the salt, which is the CaCO3. So from here, the per mole and the mole going to be cancelled out, and lastly we're going to get the unit of gram per dm cube. Okay, and by calculating the molar mass of CaCO3, we gotten the molar mass to be 100.1 gram per mole. So in order to find the solubility in gram per dm cube, we need to multiply our S value here with 100.1. So lastly, the solubility in gram per dm cube going to be 5.30 times 10 to the power of negative 3. Alright. Now we're going to look into another part, which is the idea of predicting the precipitation, iaitu pemendakan. So in order to predict precipitation, a quantity called the ionic product Q is compared to the solubility product, which is the KSP. So let's say if you have an ionic solid here. When it is in equilibrium, it's going to produce M plus aqueous ion as well as the A minus aqueous ion, the same as what we have seen before. And in order for us to compare Q and KSP, it basically means the same thing, in which the KSP equal to the M plus concentration multiplied by the A minus concentration. Meanwhile, the Q basically refers to the same thing. However, the K refers to the situation at equilibrium. Meanwhile, Q is referring to any point of the reaction, and usually it is not in the state of equilibrium, and we're going to take it at the initial point. So, in order to predict precipitation, dia mendak atau tidak mendak, we need to compare the value of Q with the KSP. So, let's say if your value of Q is equal to KSP, it basically meant the solution is saturated. And there's going to be an equilibrium that's going to be existing between the undissolved solid salt with its dissolved ion. So, berlakunya keseimbangan antara solid dan juga ions. So, what's going to happen if Q is lesser than KSP? Okay, so when Q is less, it means that the concentration of the ion here will be less as well. Okay, so you can imagine here to be lesser. So what's going to happen here is that there's going to be a shifting to the right according to the Le-Chatelier's principle in order to increase the concentration of this ion. And as a result, there's going to be no precipitation because it's going to be dissolving more. Tiada pemandakan pasal yang solid tadi telah berubah menjadi ions. Okay, and more salt should be dissolved in order to increase the concentration until Q is equal to KSP. So what happens if we have the situation of Q greater than KSP? Okay, so as what you can see here, when Q is big, the concentration of M plus and A minus is going to be big as well. So this side here will have a very, very high concentration. Okay, and it means that this solution is super saturated with the ions here. And according to the Le-Chatelier's principle, we need to shift the situation to the left. Okay, in order to reduce the ions. And as a result, the concentration of the Ma will get higher, and therefore there's going to be a precipitation. Alright? And the precipitation will decrease the concentration of the ions until the ionic product Q equals to the KSP, and when the equilibrium is established. Okay, so now we're going to look into the example on how we can apply Q with KSP. So let's say if we have 500 ml of the 0.014 molar of the CaCl2 added to the 250 ml of 0.25 molar of Na2SO4 will a calcium sulfate precipitate form. So for this reaction, it basically involves CaCl2 solution, which is in the aqueous state, reacting with the Na2SO4, which is the aqueous state as well. When they react together, what they're going to produce is the ions of the calcium sulfate, which is the CaSO4 aqueous plus NaCl, which is also in the aqueous state. And since they have 2 Cl and 2 Na, so we're going to put the 2 here in order to balance the equation. So for this reaction where CaCl2 and Na2SO4 react together, we're going to get this equation here. And we're going to put the balancing of 2 up here. Okay. However, what we are interested in is the salt of the calcium sulfate here. Okay, so we need to determine whether the calcium sulfate will be precipitated or not. Okay, so in order to further visualize this situation, you can imagine it to be something like this. So let's say if you have 500 ml of the 0.014 molar of the CaCl2 added to the 250 ml of the 0.25 molar of the Na2SO4, will the CaSO4 precipitate form or not? Okay, so when they two mix together, the volume gonna get higher. So they're gonna get a new volume which is Vt, which is 500 plus 250, it's gonna be 750 ml. So what you are interested in is the precipitate of the CaSO4. So if the CaSO4 is in the saturated solution, it's gonna form an aqueous ion. It's gonna be an equilibrium with its aqueous ion, which is the Ca2 plus aqueous as well as the SO4 2 minus. And for this reason, we need to calculate the value of Q first and compare that with our Ksp. Okay, so in order to find the value of Q, we need to get the concentration after these two mixture are being mixed. Okay, bila dah dicampurkan, dia akan memberi concentration of the Ca2 plus as well as the SO4 2 minus. And therefore, we're going to find the new concentration by using M1V1 equal to M2V2 because the V2 has been changing. So let's say if we were to find the concentration of the Ca2 plus, we're going to do M1V1 equal to M2V2. Initially, the concentration of the Ca is 0.014, which is gotten from this initial, which is here, 0.014, and the initial volume is 500. And then we need to find the new concentration. And for the volume here, it's going to be the summation of this reaction together in order to produce this solution, which is 750 ml. So once we do the maths here, we're going to get the new concentration of the Ca2 plus after mixing to be 0.093 molar. Next, we're going to find the concentration of the SO4 2 minus using a similar step. So initially, the concentration of SO4 2 minus is 0.25 molar. Okay, because SO4 2 minus is coming from these ions here, from this solution here at the beginning. Okay, so 0.25. Volume here is 250 ml. We need to find the new concentration. And the last volume after mixing is 750 ml. So once we do the math, we're going to get the new concentration to be 0.083 molar. Okay, so here are the concentration after they're being mixed together. And this will allow us to find the value of Q. Okay, so when the CaSO4 solid dissolve in order to make its aqueous ion, it's going to dissociate to form S and S concentration. So this S concentration referred to the here. So we can find the Q, which is the Ca2 plus aqueous, multiplied by its respective ion, which is SO4 2 minus. So the concentration of the Ca2 plus is 0.093. Meanwhile, the concentration of SO4 2 minus is 0.083. So once we do the multiplication, we're going to get our ionic Q to be 7.72 times 10 to the power of negative 4. So this happens at the initial stage. And we can compare the value of Q with the Ksp. So given Ksp, which is at the state of equilibrium, we're going to get 2 times 10 to the power of negative 4. From here, you can compare that our Q is greater because the power here is the same. So we're going to look into the magnitude here. So Q will be greater than the Ksp. So when Q is greater than Ksp, we know that the concentration of the Ca2 plus and the sulfate ion going to be very, very high. So when the concentration of the ions is very, very high, it means that the solution is supersaturated and it's going to shift to the left. And therefore, the precipitate going to be 4. Alright. So now for example number 2, we need to determine whether a precipitate will be formed when 100 ml of the 1 times 10 to the power of negative 3 molar of the MgCl2 is added to the 400 ml of 1.5 times 10 to the power of negative 3 molar of the NaOH. So when these two solutions mix together, they're going to form a new solution with a new volume, which is the volume total here going to be 100 plus 400, which is the 500 ml. And this reaction between the MgCl with NaOH will create the solution of the MgOH2 as well as the NaCl aqueous ions. And we're going to put a stoichiometry here in order to balance the equation. And what we are interested in is the concentration or the species of the MgOH2 here, in which we're going to compare the Q after they has been mixed with the KSP. And this is how we can determine the precipitation of the MgOH2 for this reaction. So as usual, as mentioned, we are interested in the MgOH2 solid. So it's gonna be at the stage of equilibrium with the Mg2 plus aqueous ion as well as the 2 hydroxide aqueous ion, and we can find the new concentration when they has been mixed together. So we need to use M1V1 equal to M2V2. So for the concentration of the Mg2 plus, we can substitute their value, the molarity of M1 to be 1 times 10 to the power of negative 3, because magnesium 2 plus is coming from the MgCl2. And for our new concentration, our V2 here going to be 500 ml. And then once we do the maths here, we're going to get the new concentration after they've been mixed to be 2 times 10 to the power of negative 4 molar. And now we're going to repeat the same process for the hydroxide ion, which is M1V1 equal to M2V2. So at the hydroxide ion is coming from the NaOH. So our initial concentration M1 going to be 1.5 times 10 to the power of negative 3. Our volume at the initial stage going to be 400 ml. After they have been mixed together, it's going to get a new volume, which is 500 ml. So our new concentration here to be 1.2 times 10 to the power of negative 3 molar. So here are the total concentration coming from this solution. And as mentioned, the solubility equilibrium for the magnesium hydroxide is MgOH2 solid to be in equilibrium with the Mg2 plus aqueous ion as well as 2OH aqueous ion. And at the equilibrium, we're going to produce the molar solubility of S as well as the 2S following the stoichiometry. And S here refer to 2 times 10 to the power of negative 4 molar. Okay, and the 2S here is equal to this 1.2 times 10 to the power of negative 3. Okay, so we can take it straight away from the calculation that we have made. You don't have to multiply it with 2 here. Okay, kita tak perlu buat macam ini. Kenapa? Because the 2OH minus here is coming from the solution of the NaOH, which is we have calculated it. So the total concentration of OH minus has been included, and therefore we doesn't have to multiply it by 2 again. Alright, so in order to find the value of Q, we need to write the expression first, which is Mg2 plus multiplied by the hydroxide ion to the power of 2. So the number 2 is still maintained because of the stoichiometry. And then for the concentration of the Mg2 plus, we're going to substitute 2 times 10 to the power of negative 4. For the hydroxide, we can straight away take it from here, which is 1.2 times 10 to the power of negative 3. And then don't forget to square it. Okay. And then once we do the math, we're going to get our Q to be 2.88 times 10 to the power of negative 10. And from here, we can compare the value of Q with KSP, in which our Q going to be greater than KSP because it is to the power of negative 10. Our KSP given is to the power of negative 11. And therefore, we can say that the value of Q is greater than KSP. So when our value of Q is higher, it means that the concentration of the ions here are going to be higher. And according to the Le-Chatelier principle, we're going to reduce it back by shifting it to the left. Okay.
And because the concentration here is very high at the initial stage, we can say that the solution is super saturated. And in order to reduce it, we need to shift it to the left so that the precipitate of the MgOH2 can be formed. Alright,
So I think that's all for this video. See you again some other time. Bye!